Professor Dave and Chegg here, we know a bit about ethers, but there is a specific subset of ethers called epoxides, or oxiranes, which have some interesting properties that we will want to understand. So let's get a closer look at epoxides now.
So what are epoxides exactly? Well, they are cyclic ethers, sort of like tetrahydrofuran or 1,4-dioxane, which are common solvents. However, epoxides are a bit different. Epoxides are three-membered rings with oxygen at one of the positions. Again, given that this oxygen atom has alkyl on either side, epoxides qualify as ethers, though they are cyclic ethers. Here is the simplest epoxide, oxycyclopropane, also known as ethylene oxide, though the proper IUPAC name would be 1,2-epoxyethane. A very common way to make epoxides is by using an alkene starting material and a reagent called metachloroperoxybenzoic acid, or MCPBA. It's a peroxybenzoic acid because of the peroxy functional group, so instead of the typical OH in this part of the carboxyl group, we have OOH. The second oxygen is the one that gets incorporated into the epoxide. We won't discuss the mechanism. For now, we just have to be familiar with the name of the reagent and know that it will turn an alkene into an epoxide because one of these oxygen atoms in this functional group will get transferred into this pi bond. Another way to get an epoxide is to form a halohydrin, which means a hydroxyl and a halogen on adjacent carbons. This can form when performing halogenation in the presence of water, as water can attack the intermediate instead of the halide ion to produce the halohydrin. Then base can be used to deprotonate the hydroxyl, and the resulting oxyanion can attack the carbon that bears the halogen in SN2 fashion, since the stereochemistry allows for the backside attack, and the halogen is kicked off, yielding the epoxide.
We will see epoxides sporadically throughout our study of organic chemistry, so now we know what they are and how to make them. Professor Dave for Chegg. See you next time.